Today and for the next 2 weeks, we're going to be studying what for many engineers and a few scientists is the most popular method of solving any differential equation that of the kind that they happen to meet, and that is to use the popular machine called the Laplace transform. Now, you'll get proficient in using it by the end of the 2 weeks. But there's always a certain amount of mystery that hangs around it, and people scratch their heads and can't figure out where it comes from. And that bothers them a lot. In the past, I've usually promised to tell you at the end of the students at the end of the 2 weeks, but I almost never have time, so I'm going to break that glorious tradition and tell you up front at the beginning where it comes from, and then talk very fast for the rest of the period. Okay. A good way of thinking of where Laplace transform comes from, in a way which I think dispels some of its mystery, is by thinking of power series. I think virtually all of you have studied power series, except possibly a few students who just had 1801 here last semester and probably shouldn't be taking 1803 anyway now. But anyway, a power series looks like this: summation an x to the n, and you sum that from, let's say, 0 to infinity. And the typical thing you want to do with it is add it up to find out what its sum is. Now, the only way I'll depart from tradition, instead of calling the sum some generic name like f of x, in order to identify the sum with the coefficients a, I'll call it a of x. Now, I want to make just one slight change in that. Slight change in this. I want to use computer notation, which doesn't use a subscript a sub n. Instead, it thinks of as a function of the discrete variable n. In other words, it's a function which assigns to n equals 0, 1, 2, 3, real numbers. That's what these sequence of coefficients really is. So in computer notation, it will look almost the same. It's just that I'll write this in functional notation as a of n instead of a sub n. But it still means the real number associated with the integer, positive integer, n. And everything else is the same. See, what I'm thinking of this as doing is taking this discrete function, which gives me the sequence of coefficients of the power series, and associating that with the sum of the power series. Let me give you some very simple examples, two very simple examples which I think you know. Suppose this is the function 1. Now, what do I mean by that? I mean it's the constant function 1. To every positive integer, it assigns the number 1. Okay, what's a of x? What I'm saying is, in other words, in this fancy mystifying form, if all of these guys are 1, what's a of x? 1 plus x squared plus x cubed. Look, you were supposed to be born knowing what that adds up to. It adds up to 1 over 1 minus x. Except that's the wrong answer. What's wrong about it? It's not true for every value of x. That's only true when x is such that that series converges, and that is only true when x lies between -1 and 1. So it's not this function, it's this function with its domain restricted to be less than 1 in absolute value. What does that converge to if x is bigger than 1? The answer is it doesn't converge. It's nothing. There's nothing to add up else you can put here. Okay, let's take another function. Suppose this is, let's see, 1 over n you probably won't know. Let's take one you will know. 1 over n factorial. Suppose a of n is the function 1 over n factorial. What's a of x? So what I'm asking is, what does this add up to when the coefficient here is 1 over n factorial? What's summation x to the n over n factorial? It is e to the x. And this doesn't have to be qualified because this is true for all values of x. So in other words, from this peculiar point of view, I think of a power summing, the operation of summing a power series as taking a discrete function defined for positive integers or non-negative integers and doing this funny process, and out of it comes a continuous function of some sort. And notice what goes in is the variable n, but what comes out is the variable x. Well, that's perfectly natural. That's the way a power series is set up. So the question I ask is here, this is a discrete situation, a discrete summation to get this function A. Suppose I made the summation continuous instead of discrete. So I want the continuous analog. Of what I did over there. Okay, what would the continuous analog be? Well, instead of I'll replace n0, 1, 2, that will be replaced by a continuous, that's a discrete variable. I'll replace it by a continuous variable t, which runs from 0 to infinity. And is allowed to take every real value in between instead of being only allowed to take the values at the positive integers, non-negative integers. Okay, well, if I want to use t instead of n, I clearly cannot sum in the usual way over all real numbers, but the procedure which replaces summation over all real numbers is integration. So what I'm going to do is replace that sum by the integral from 0 to infinity. That's like the sum from 1 to infinity, from 0 to infinity, of what? Well, of some function, but now n is being replaced by the continuous variable t, so this is going to be a function of t. And how about the rest of it? The rest I'll just copy. X to the nth, well, instead of n, I have to write t, and dt. And what's the sum? Well, I'll call the sum, what's the sum a function of? I integrate out the t, so that doesn't appear in the answer. All that appears is this number x, this parameter x. For each value of x, like 1, 2, or 26.3, this integral has a certain value, and I can calculate it. So this is end up as a function of x, just as it did before. Now, I could leave it in that form, but it would be, no mathematician would like to do that, and very few engineers either. The reason is, in general, when you do integration and differentiation, you do not want to have as the base of an exponential something like x. The only convenient thing to have is e, and the reason is because it's only e that people really like to differentiate. E to the something is the only things that people really like to differentiate or integrate. So I'm going to make this look a little better by converting x to the t to the base e. And remember how to do that. You write x equals e to the log x. And so x to the t will be e to the t log x, e to the log x times t, if you want. Now, the only problem is, I want to make one more little change. After all, I want to be able to calculate this integral. And it's clear that if t is going to infinity, if I have a number here, for example, like x equals 2, that integral is really quite unlikely to converge. For example, if a of t were just the constant function 1, the integral certainly wouldn't converge. It would be horrible. That integral only has a chance of converging if x is a number less than 1, so that when I take bigger and bigger powers of it, I get smaller and smaller numbers. Don't forget, this is an improper integral going all the way up to infinity. Those need treatment, delicate handling. All right, so I really want x to be less than 1. Otherwise, that integral is very unlikely to converge. I better have it positive, because if I allow it to be negative, I'm going to get into trouble with negative powers. See, what's minus 1, for example, to the 1/2, when t is 1/2? That's already imaginary. I don't want that. If you've got an exponential, the base has got to be a positive number. So I want x to be a positive number. All right. If x in my actual practice is going to lie between 0 and 1 in order to make the integral converge, how about log x? Well, log x, if x is less than 1, then the log of 1 is 0. So log x is going to be less than 0, and it's going to go all the way down to negative infinity. So this means log x is negative. In this interesting range of x, the log x is always going to be negative. And now, I don't like that. In the first place, I'd like to call this by a new variable since no one uses log x as a variable. And it would make sense to make it a negative. To make it negative, that is to write log x is equal to negative s. Let's put it on the other side. In order that since log x is always going to be less than 0, then s will always be positive, and it's always more convenient to work with positive numbers instead of negative numbers. So if I make those changes, what happens to the integral? Well, I stress, all these changes are just cosmetic to make things a little easier to work with in terms of symbols. First of all, the a I'm going to change. I don't want to call it a of t because most people don't call functions a of t. They call them f of t. So I'll call it f of t. X is e to the log x, which is e to the minus s. So x has had its name changed to e to the minus s. In other words, I'm using as the new variable not x any longer, but s, in order that that base be e. T, I now raise this to the tth power, but by the laws of exponents, that means I simply multiply the exponent by t. And dt. And now, since I'm calling the input function f of t, the output ought to be called capital F, but it's now a function, since I've changed the variable, it's now a function of s. It's no longer a function of x. If you like, you may think of this as a of, what's x? X is e to the negative s, I guess. I mean, no one would leave a function in that form. It's simply a function of s. And what is that? So what do we got, finally? What we have, dear hearts, is this thing, which, I stress, is nothing more than the continuous analog of the summation of a power series. This is the discrete version. This is, by these perfectly natural transformations, the continuous version of the same thing. It starts with a function defined for positive values of t and turns it into a function of s. And this is called the Laplace transform. Now, if I've done my work correctly, you should all be saying, oh, is that all? But I know you aren't, so it's okay. You'll get used to it. The first thing you have to get used to is one thing some people never get used to, which is you put in a function of t and you get out a function of s. How could that be? You know, for an operator, you put in 3x and you get out 3 if it's a differentiation operator. In other words, when you have an operator, the things we've been talking about for the last 2 or 3 weeks in one form or another, at least the variable doesn't get changed. Well, but for a transform it does, and that's why it's called a transform. So the difference between a transform and an operator is that for a transform, a function of t comes in, but a function of s comes out. The variable gets changed, whereas for an operator, f of t goes in, and what comes out is g of t, a function using the same variable, like differentiation. This is a typical example of an operator. Or the linear differential operators we've been talking about. Well, but this doesn't behave that way. The variable does get changed. That's, in fact, extremely important in the applications. In the applications, t usually means the time, and s very often, not always, but very often is a variable measuring frequency, for instance. So that's a peculiar thing that's hard to get used to. But a good thing is the fact that it's a linear transform. In other words, it obeys the laws we love and like, that the Laplace transform. Oh, I never gave you any notation for the Laplace transform. Hey, I better do that. Okay, so some notation. There are 2 notations that are used. Your book mostly uses the notation that the Laplace transform of f of t is capital F of s. Uses the same letter, but with a capital F, same capital. Now, as you'll see, there are some places you absolutely you cannot use that notation. It may seem strange looks perfectly natural. There are certain laws you cannot express using that notation. It's baffling. But if you can't do it this way, you can do it using this notation instead. One or the other will almost always work. So I'll use my little squiggly notation. That's what I use. I think it's a little more vivid. And the trouble is this piles up too many parentheses, and that's always hard to read. So I like this better. So these are two alternate ways of saying the same thing. That the Laplace transform of this function is that one. Okay, well, let's use, for the linearity law, it's definitely best. I really cannot express the linearity law using the second notation, but for using the first notation, it's a breeze. That the Laplace transform of the sum of two functions is the sum of their the sum of the Laplace transforms of each of them separately. Or better yet, write it. You could write it that way, or let's write it this way. That way, it looks more like an operator: L of f plus L of g. And the same way, if you take a function and multiply it by a constant, and take the Laplace transform, you can pull the constant outside. And of course, why are these true? These are true just because of the form of the transform. If I add up f and g, I simply add up the two corresponding integrals. Integral, in other words, I'm using the fact that the integral, this definite integral, is itself a linear operator. Okay. Well, that's the general setting. That's where it comes from, and that's the notation for it. And now we have to get to work. The first thing to do to get familiar with this is, obviously what we want to do is say, okay, these were the transforms of some simple discrete functions. Okay, suppose I put in some familiar functions, f of t. What do their Laplace transforms look like? So let's do that. One of these boards I should keep store. Why don't I store on this board? I'll store on this board the formulas as we get them. So let's see, what should we aim at first? Let's first find, and I'll do the calculations on the sideboard so that, I won't, we'll see how it works out. I'm not very sure. In other words, what's the Laplace transform of the function 1? Well, there's an even easier one. What's the Laplace transform of the function 0? Answer, 0. Very exciting. What's the Laplace transform of 1? Well, it doesn't turn out to be a constant any more than it turned out to be a constant up there. Let's calculate it. Now, you can do these calculations carefully, dotting all the i's, or pretty carefully, or not carefully at all, i.e. sloppily. I'll let you be sloppy after. Generally speaking, you can be sloppy unless the directions tell you to be less sloppy or to be careful, okay? So I'll do one carefully. Let's calculate the Laplace transform of 1. Carefully. Okay? In the beginning, you got nothing to use with the definition, so I have to calculate the integral from 0 to infinity of 1, that's the f of t, times e to the negative st, so I don't have to put in the 1, dt. All right. Now, let me remind you, this is an improper integral. This is just about the first time in the course we've had an improper integral, but there are going to be a lot of them over the next couple of weeks. Nothing but. All right, it's an improper integral. That means we have to go back to the definition. If you want to be careful, you have to go back to the definition of improper integral. So it's the limit as r goes to infinity of what you get by integrating only up as far as r. That's a definite integral. That's a nice Riemann integral. So this is what I have to calculate. And then I have to take the limit as r goes to infinity. Now, how do I calculate that thing? Well, this integral is equal to, that's easy. It's just integrate. Remember that you're integrating with respect to t. So s is a parameter. It's like a constant, in other words. So it's e to the minus st. And when I differentiate it, the derivative of this would have negative s. So to get rid of that negative s, so the derivative is e to the minus st, you have to put a minus s in the denominator. And now I'll want to evaluate that between 0 and r. And what do I get? Well, it is at the upper limit. So it's e to the minus s times r minus, at the lower limit, it's t is equal to 0. So whatever s is, it's 1. And that's divided by this constant out front, negative s. So the answer is, it is equal to the limit of, as r goes to infinity, of e to the negative sr minus 1 divided by minus s. Now what's that? Well, as r goes to infinity, e to the minus, like minus 2r or minus 5r goes to 0, and the answer is minus 1 over minus s, so that's 1 over s. And so that's our answer. Let's put it up here. It's 1 over s, except it isn't. I made a mistake. Well, not a mistake, a little oversight. What's the oversight? This is okay. This is okay. This is okay. This is not okay. This is okay, but that's not okay. What's wrong? You know, I did sleight of verbal hand. Maybe some of you picked it up and were too embarrassed to correct me. But, you know, I said, like e to the minus 2r obviously goes to 0, and e to the minus 5r goes to 0. How about e to the minus 3r? Does that go to 0? No, that's e to the 3r, which goes to infinity. The only time this goes to 0 is if s is a positive number. Minus s looks like a negative number, but it's not if s is equal to minus 2. So this is only true if s is positive. Because only if s is positive is this exponent really negative and large, and therefore going to infinity, going to 0 as r goes to infinity. So the answer is not 1 over s, it is 1 over s, s must positive. Now, once again, here, people who don't worry about this sort of thing with power series because it seems very obvious, you know, 1 over x, absolute value of x less than 1. When it gets to be the Laplace transform, just because the Laplace transform is mysterious, the question is, okay, the Laplace transform is 1 over s when, of 1, the Laplace transform 1, I understand, is 1 over s, s if s is positive. What is it if s is negative? Okay, write down in your little books, this, right, put that down. What is it if s is negative? And right underneath that, this question is meaningless. Doesn't mean anything. All I'm saying is it's the Laplace transform. I'll draw you a picture. This is a picture of the Laplace transform of 1. It is that. It's a one branch of this curve. It does not include the branch on the left. It doesn't because I showed you it doesn't. That's all there is to it. Okay, so I did that carefully. Now I'm going to get a little less careful. What's the Laplace transform of e to the at? First of all, in general, the kind of functions for which people like to calculate the Laplace transform, and basically the only ones that will be in the tables, are exactly the sort of functions that you used in solving linear equations with constant coefficients. What kinds of functions entered in there? Exponentials, sines and cosines, but they were really complex exponentials, right? E to the t sine t, but that was really a complex exponential too, just a little more complicated one. Polynomials, and that's about it. T times e to the t, that was okay too. These are the functions for which people calculate the Laplace transforms, and all the other functions, they don't calculate Laplace transforms of. So I don't mean to disappoint you. You're going to say, oh, what? That same old stuff. For 2 more weeks, we got that same. Well, the Laplace transform does a lot of things much better than the methods we've been using, and I'll sell it when I get a chance to. For now, let's just get familiar with it. All right, so I'm not going to calculate e to the at for you because I'd like instead to prove a simple formula which will give that and a lot, will also give us e to the at sine t. It will give us a lot more instead. I'm going to calculate a formula for the Laplace transform of this guy if you already know the Laplace transform of f. Now, you can see this falls in that category because this is really e to the at times 1, but I already know the Laplace transform of 1. So that's, if I can get a general formula for this, I'll be able to get the formula for e to the at as a consequence. So let's look for this Laplace. Now, it's really easy. Let's see, where am I doing calculations? Over here. Okay, so we got e. So I want to calculate the Laplace transform of e to the at f of t. So I'm going to say that's the integral from 0 to infinity of e to the at times f of t. And now the rest I copy. It's times, that's the function part of it that goes the input. And then there's the other part. This part is called the kernel, by the way, but don't worry about that. However, if you drop it in conversation, people will sort of look at you and say, gee, they know something I don't. And you will. You know that it's the kernel. Okay. Well, now, what kind of a formula could I be looking for? Clearly, I could only be looking for a formula which expresses it in terms of the Laplace transform of f of t. But let's calculate it and see what we get. Now, what would you do to that thing to make? Well, obviously, what the thing to do is to combine the two exponentials. So that's going to be the integral from 0 to infinity of f of t e. Now, I'd like to put it, to combine the exponentials in such a way that it has still that same form. So I'm going to begin with a negative sign and then see what the rest of it has to be. What is it going to be? Well, minus st and plus at, but I can make that minus a here, and it'll come out right. So it's minus st plus at, and there are the two parts, those two factors. dt. So what's that? That's a Laplace transform. If the a weren't there, this would be the Laplace transform of f of t. What is it with the a there? It's the Laplace transform of f of t, except that instead of the variable s has been replaced by the variable s minus a. Give you a second to digest that. Well, you digest it while I'm writing it, because that's the answer. And the way this is most often used, I have to qualify it for the value. So if f of s is good for s positive, the way it would be, for example, if I use the function 1 here, then to finish that off, then f of s minus a will be good when s is bigger than a. Why is that? Well, because this is true if s minus a is positive. That's the condition. That's when this Laplace transform is good. But that simply says that s should be bigger than a. And since this doesn't look pretty, let me try to make it look a little prettier. So let's write it. So this is assuming f of s is for s greater than 0. Now, this is called something. This is called the, well, what would you call it? On the left side, you multiply by an exponential. On the right, you translate, you shift the argument over by a. So this is called, gulp, the exponential shift. What? Well, I'll call it the formula. The thing before, when we talked about operators, we called it the exponential shift rule or the exponential shift law. But in fact, this is, in a way, a disguised form of the same law. And engineers who typically do all their work using the Laplace transform and don't use operators, this is the form of the exponential shift law that they would know. What you can do with one, you can do with the other. You can now use both. So what's the answer to e to the at? Well, the answer is, I'm supposed to e to the at times 1. The Laplace transform of 1 is 1 over s. And therefore what I do is, to multiply by e to the at, I change s to s minus a. And so that's the answer. Let's see, what else don't we know? Well, how about sines and cosines? Well, the way to do sines and cosines is by making the observation that this formula also works when a is a complex number. So can use also for a complex number, for e to the a plus bi times t. The Laplace transform of e to the a plus bi times t is 1 over s minus a plus bi. And again, it will be for s bigger than a. So let's calculate the Laplace transform of, let's say, well, I got to cover up something. Okay, so that's the Laplace transform. Got to remember that. So let's calculate the Laplace transform of, let's say, sine of at and cosine at. What do you get for that? Well, just for a little variety, we could do it by using that formula and taking its real and imaginary parts. I'm going to, since some of you had so much difficulty with the backwards Euler formula, here's a good case where you could use it. Suppose you want to calculate the Laplace transform of cosine at. Well, I'm going to write that using I want to calculate it using complex exponentials. And the way I'll do it is by using the backwards Euler formula. So this is e to the iat plus e to the minus iat divided by 2. Remember, the forward Euler formula would say e to the iat equals cosine at plus I sine at. That expresses the complex exponential in terms of sines and cosines. This is the backward formula, which just reads it backwards, expressing cosines and sines in terms of complex exponentials instead. Both formulas are useful, almost equally useful, in fact. And anyway, just to remind you of it, let's use this one. Okay, what's the Laplace transform then of cosine at? Well, by linearity, it's equal to 1/2 the Laplace transform of this guy plus the Laplace transform of that guy. And what are those? Well, the Laplace transform of e to the iat is 1 over s minus ia. And the Laplace transform of the other guy is 1 divided by s plus ia. Now, of course, this has to come out to be a real function. This is real. The integral is real. This must come out to be real. This looks kind of complex, but it isn't. I know automatically that this is going to be a real function. How do I know that? Well, mentally you can combine the terms and calculate it, but I know even before that. Remember, there are two ways to see that something is real. You can see that you can calculate it and see that its imaginary part is 0, hack. Or, without any calculation, if you change I to minus I and you get the same thing, it must be real. Now, if I change I to minus I in this expression, what happens? If I change I to minus I, this term turns into that one, and this one turns into that one. Conclusion that the sum of the two is unchanged. And therefore, this is real. Well, of course, in the time I took to make that argument, I could have actually calculated it. So what the heck, let's calculate it. So, you do the high school thing, and it's this plus that, this guy plus that guy on top, which makes 2s. And on the bottom is the product of those, which by now you should know the product of two complex numbers. A product of a number and its complex conjugate is sum of the squares. So what's the answer? The 2's cancel, and the answer is that the Laplace transform of cosine AT is S over S squared plus A squared. And that will be true, as in general is true up there, for positive values of S only. And the sine AT, you can calculate that in recitation tomorrow. The answer to that is A divided by S squared plus A squared. You would get the same answers if you took the real and imaginary parts of that expression. It's another way of getting at the recitations tomorrow will give practice in calculating other functions related to these by using these formulas, and also from scratch directly from the definition of Laplace transform. Well, there are two things which we still should do. The first is I want to get you started with calculating inverse Laplace transforms. And the reason for doing that is, in other words, I've started with f of t, and we've been focusing on is what is capital F of s. But you'll find that when you go to solve differential equations, by far the hardest part of the procedure is you get f of s, the Laplace transform of the answer, and you have to convert that back into the answer in terms of t that you were looking for. In other words, the main step in the procedure that you're going to be using for solving differential equations is, and the hardest part of the step will be to calculate inverse Laplace transforms. Now, you think that can be done by tables, but in fact, it can't unless the tables are too long to be useful. You have to do a certain amount of the work yourself. And the certain amount of the work that you have to do yourself involves partial fractions decompositions. And in case you were wondering, which you were not, the reason you learned partial fractions in 1801 was not to do those silly integrals, but you learned it so that when you got to 1803, you would be able to solve differential equations by using Laplace transforms. Sorry, that's life. Now, so a certain amount of the recitation time tomorrow will be devoted to reminding you how to do partial fractions, since you haven't done it in a while, and I assume it's, yeah, we had that, I think. Okay. Now, they will also remind you of the most efficient method, which about half of you have had, and the rest think you might have had, but really aren't sure. When the bottom, so here's the S, and we want to find out what its inverse Laplace transform is. What you have to do, it normally won't be in the tables like this. You have to put it in a form in which it will be in the tables. And to do that, you have to make the partial fractions decomposition, which, to do it quickly, so if you don't know what I'm doing now, or think you once knew but don't quite remember, go to recitation tomorrow. To get the coefficient here, I cover up S, and I put S equals 0, because that's the law. To get this coefficient, I cover up S plus 3, and I put S equal to negative 3, because that's what you're supposed to do. Put S equal negative 3, you get minus 1/3. This is equal to that. In this form, I don't know what the inverse Laplace form is, but in this form, I certainly do know what the inverse Laplace transform, because the inverse Laplace transform is linear, and because each of these guys essentially occurs in those tables. What's this? Well, it's whatever the Laplace transform of, inverse Laplace transform of 1 over S is, multiplied by 1/3. Well, the inverse Laplace transform of 1 over s is 1. So it's 1/3. 1/3 times 1. How about the other guy? Minus 1/3. The inverse Laplace transform of 1 over s plus 3. That's this formula. A is -3. And that makes e to the minus 3t. So if this was the Laplace transform of the solution to the differential equation, then the solution in terms of t was this function. Now you'll get lots of practice in that. All I'm doing now is signaling that that's the most important and difficult step of the procedure, and that please start getting practice, get up to snuff doing that procedure. Okay, in the time remaining, I want to add one formula to this list, and that is going to be the Laplace transform of, we still haven't done polynomials, and now to do polynomials, because the Laplace transform is linear, all I have to do is know what the Laplace transform of the things, the terms, the individual term of a polynomial. In other words, what's the Laplace transform of t to the n, where n is some positive integer? Well, let's bravely start trying to calculate it. Integral from 0 to infinity, t to the n, e to the negative st dt. Now, I think you can see that the method you should use is integration by parts, because this is a product of two things, one of which you would like to differentiate a lot of times, in fact, and the other won't hurt to integrate it because it's very easy to integrate. So this factor is going to be the one that's to be differentiated, and this is the factor that will be pleased to integrate it. Let's get started and see what we can get out of it. Well, this time I'm going to be, well, no, I better be a little careful because there's a point here that's tricky. Okay, the first step in integration by parts is you only do the integration, you don't do the differentiation. And remember, the variable is t. The s is just a parameter, it's just a constant that's hanging around not knowing what to do. Okay, so the first step is you don't do the differentiation, you only do the integration. Evaluate it between limits, and then you put a minus sign before you forget to do it, and then integral 0 to infinity. Now you do both operations, so it's n t to the n minus 1, and you also do the integration. Okay, let's consider each of these pieces in turn. Now this piece, well, there's no problem with the limit, lower limit 0, because when t is equal to 0, this factor is 0 and the thing disappears, as long as n is 1 or higher. So it's minus 0 here at the lower limit. The question is, what is it at the upper limit? So what I have to do is find out what is the limit. The limit as t goes to infinity. That's what's happening up there, of t to the n times e to the negative st divided by minus s. Well, as t goes to infinity, this goes to infinity, of course. This had better go to 0, unless I want an answer infinity, which won't do me any good. If this goes to 0, s had better be positive, so I'd better be restricting myself to that case. Okay, so let's assume that s is positive so that this minus s really is a negative number. Okay, then I have a chance. So this is going to be the limit. Let's write it in a more familiar form with that down below. So it's t to the n, that's going to infinity, but the bottom is e to the minus st, but now it's plus st, and that's going to infinity too, because s is positive. So the two guys are racing, and the question is, oh, I lost a minus s here. So equals minus 1 over s. How's that? Let's focus on, so the question is only which guy wins. In the race to infinity, which one wins and how do you decide? And the answer, of course, is that's the bottom that wins. The exponential always wins, and it's because of L'Hopital's rule. If you differentiate top and bottom. Nothing much happens to the bottom. Gets another factor of s. But the top goes down to t to the n minus 1. Now L'Hopital it again, and again, and again, and again, and again, until finally you've reduced the top to t to the 0, where it's defenseless and just sitting there, and nothing's happened to the bottom. It's still got e to the st, and that goes to infinity. So the answer is, this is 0 by n applications of L'Hopital's rule, or if you're very clever, you can do it in 1, but I won't tell you how. So the answer is that this is 0. At the upper limit, it's also 0, at least if s is positive, which is the case we're considering. That leaves the rest of this. All right, let's pull the constants out front. That's plus. 2 negatives make a plus. N over s. And what's left? The integral from 0 to infinity of t to the n minus 1 e to the minus s t dt. But what on earth is that? That is n over s times the Laplace transform of t to the n minus 1. We got a reduction formula. We don't get the answer in one step, but we get a reduction formula. And it says that the Laplace transform, let me write it this way for the once. The first way is now better, is equal to n over s times the Laplace transform of n minus t to the n minus 1. Okay, the next step, this would be n over s times n minus 1 over s times the Laplace transform of t to the n minus 2. If I can continue, I finally get, in the top, n times n minus 1 times all the way down to 1, divided by the same number of s's, n of them, times the Laplace transform of t to the 0, finally. See, 1, 0, n minus 1. And so what's the final answer? It is n factorial over s to the what power? Well, the Laplace transform of this is 1 over s. So the answer is it's s to the n plus 1. N of them here, plus an extra 1 coming from the 1 over s here. And that's the answer. The Laplace transform of t to the n, oddly enough, is more complicated and looks a little different from these. It's n factorial over s to the n plus 1. And with that, you can now calculate the Laplace transform of anything in sight, and tomorrow you will.